Automatic, Addison.
In this tutorial, we will create a model of a robotic arm from scratch. Our robotic arm model will be in the standard Unified Robot Description format, also known as URDF. We will then visualize the robotic arm in RViz, a 3D visualization tool for ROS 2. Within ROS 2, defining the URDF file of your robotic arm is important because it allows software tools to understand the robot structure, enabling tasks like simulation, motion planning, and sensor data interpretation. It is like giving the robot a digital body that software can interact with. I will walk through all the steps for creating the URDF for the MyCobot 280 robotic arm by Elephant Robotics. Follow along with me, click by click, keystroke by keystroke. A URDF, or Universal Robot Description Format file, is an XML file that describes what a robot should look like in real life. It contains the complete physical description of the robot. Building the body of the robot is the first step when integrating your mobile robot or robotic arm with ROS 2. The body of a robot consists of two components, links and joints. Links are the rigid pieces of a robot. They are the bones. Links are connected to each other by joints. Joints are the pieces of the robot that move, enabling motion between connected links. So consider the human arm that you see in this image as an example. The shoulder, elbow, and wrist are joints. The upper arm, forearm, and palm of the hand are links. For a robotic arm, links and joints look like this. You can see that a robotic arm is made of rigid pieces, links, and non-rigid pieces, the joints. So servo motors at the joints cause the links of a robotic arm to move. So I'll repeat that. For a robotic arm, you've got links and joints. It looks just like this image. So links are these hard, rigid pieces, and then the non-rigid pieces, the pieces that move where your servo motors are, okay? Those are the joints. And it's the motion of the joints that cause the links to move. It's the motors inside the joints that make the links move. So links are connected by joints, and it's that motion at the joint area that causes the links to move, just like where your elbow is, where your wrist is, and where your shoulder is. So for a mobile robot with LiDAR, links and joints look like this. In this case, the non-rigid pieces are the wheel joints, and these wheel joints are revolute joints. Why? Because they revolve. They move around and around and around. And so those revolute joints cause rotational motion. The wheel joints in the photo connect the wheel link to the base link, and the base link, that's a rigid piece. So fixed joints have no motion at all. You can see that the LiDAR, the laser scanner up there on top of this mobile robot, is connected to the base of the robot via a fixed joint. This could be a simple screw that connects the LiDAR to the base of the robot. You can also have prismatic joints. Prismatic joints. So this would be common in a XACRO robot. And prismatic joints cause linear motion between links as opposed to rotational motion. The first step is to create a ROS 2 package to store all of your files. So I have a terminal window open, and let's create a new folder named mycobot_ROS2. So I'm going to first go into the workspace, the source folder, and in the source folder we do make dir, as in make directory, and then mycobot_ROS2. Enter. Now let's move inside there. And all right, so now let's create the package where we will store our URDF file. This is the model of the robot. And by convention, we call this package whatever the name of your robot is, and then underscore description. You'll see that all across the ROS community. It'll be the name of the robot underscore and description. That by convention is where you will store the model, the URDF file for your robots. And let's do that now. So we'll do ROS to PKG as in package, create, and then hyphen, build type, amend, CMake, and then license. And we'll do BSD3 clause. All right, and then my cobot underscore description. And there it is. Let's see if it's in there. There it is, my cobot description. Now let's create what's called a meta package. A meta package doesn't contain anything except a list of dependencies to other packages. You can use a meta package to make it easier to install multiple related packages at once. So for example, if you were to make your package available to install publicly using the apt-get package manager on Ubuntu, for example, a meta package would enable someone to automatically install all the ROS2 packages that are referenced in your meta package. It's going to clear, and I'm going to do ROS2 package, create, build, type, amend, CMake, license, BSD3 clause. Okay, and BSD3 clause, you can look that up on Wikipedia about what that means, what permissions that sets on your package, but essentially means you can modify, distribute this package any way you'd like. So now I'm going to do, by convention, the name of the meta package is the name of the folder that you put your code in. So I'm going to do the my cobot underscore ROS2. This will be my meta package. Okay, and the first order of business is let's configure the package XML file. So get it, package, oh, got to move into it first. CD my cobot ROS2, clear. Let's see if our package is in there. So I'm going to do get it, package.xml. And let's take a look at this. Take a look. Okay, so name of the package is fine. Excuse me. Description, let's put a good description here. So I'm going to say my cobot series robots by Elephant Robotics, and let's say meta package. Okay, everything looking good. And let's add an execution dependency, which we only have one right now, which is the description package. So we'll do exec depend, and then we'll do my cobot underscore description, and then exec underscore depend. Save. Pretty basic at this stage. Let's close it. Okay, now let's create a README file to describe what this meta package is about. All right, and we'll just create a basic one for now. So let's do get it, README. This will be a placeholder, README.md. Okay, and let's just do pound my cobot underscore ROS2. Pound. Save it. Close it. Now let's move one layer up. Now we're in our main folder. You can see here we've got our meta package and our description package. And let's create a README for this. This is the one that will show up, let's say, if you are hosting your folder on GitHub. This will be on the main page. And so let's make it nice and pretty. Let's do get it readme.md. And at the top, we'll do pound my cobot underscore ROS2. Pound. And let's make a nice, pretty icon over here. So I'm going to do exclamation point. We need to tell users what the operating system is. Now let's do an icon that shows the actual operating system. In this case, we're using Noble, Ubuntu Noble. So we'll do https://img.shields.io/v/ubuntu wallpapers/noble. Okay, and now let's tell users what the ROS2 version is. So we do ROS_2. Let's do https://img.shields.io/ROS/v/Jazzy, because we're using ROS2 Jazzy, and then RCL CPP. Nice and pretty. Save it. Okay, so now we've got our meta package, and what are we forgetting now? Oh, let's do our description package as well. So we'll do cd my_cobot description. We're in here now. You can see it's got no readme, so let's do one now. Let's do get it readme.md. I'm going to do pound my_cobot_description. Take your time. Slow is smooth, smooth is fast. We're in no rush. Enjoy the journey. Save it. All righty. Now let's go back to our workspace. cd curl ~ROS2_WS. And now we're in the workspace. Okay. And now I'm going to run our colcon build command to build all the code and all the changes we just made. Everything built just fine. We can see every package finished with flying colors. All right. Now, let's see if our package is currently recognized by the ROS2 system. To do that, you can either, at this stage, open a new terminal window like this. Okay. Or if you want to remain in the same terminal, you source the bash RC. So source ~/.bash RC. And there we go. Now do ROS2 pkg list. And let's look for it. Where are you? Where are you, my cobot ROS2 package? Where are you hiding? Here are our new packages. This is our meta package. And then we have our mycobot description package we just made. Remember, the mycobot description package, that's where we're going to put all the physical, define all the physical aspects of a robot, the geometry, the kinematics, the dynamics, all the visual aspects. We'll fill that in later. Everything's looking good because ROS2 recognizes, and look at all these packages. That's the beauty of ROS2. We've got all this code that's ready for you to use out of the box. So you don't need to reinvent the wheel all the time. Okay, and now I promised to you that we would fill out our mycobot description package. Let's type some commands right now that will help us do that. One right after the other. Okay, so the first command I want you to do is I want you to, let's go back to the root. All right, and let's do make dir p ~/ROS2 workspace source mycobot ROS2 mycobot description package. And let's create a folder for meshes. You'll learn what meshes are later. But just follow me here. We're going to create a folder called meshes. And in there, I'm going to say mycobot_280. And let's do visual. Create all of these folders and enter. Okay, now let's go here and let's create a new folder called URDF/control. All right. Let's create another one called mech. Let's create another one called sensors. This is where the sensors of the robot will go. Let's create another one called robots. All right, so we created all of our folders. It's clear. Let's talk about mesh files. Mesh files are what make your robotic arm look realistic in robotic simulation and visualization programs. Mesh files visually represent the 3D shape of the robot parts. These files are typically in formats such as STL and DAE. Now, the mesh files that we are going to use were created by Elephant Robotics. And you can see DAE, these DAE files right here. And these are mesh files. Can't visualize them in GitHub right here, but you can download and use a software tool or an online tool to actually see the visual rendering of one of these mesh files, which make the robotic arm look a lot more realistic than it otherwise would be if we didn't have the DAE or STL files. So in many cases, when you're working with the robotic arm, the manufacturer, particularly if they have a ROS2 package, they will already create these DAE or STL mesh files for you. So you don't really need to create these from scratch. However, if you wanted to create your own custom mesh files, let's say your own custom 3D printed robotic arm in the future, you can go use a program like Onshape, Fusion 360, AutoCAD, or SolidWorks, where you design the robot's body using one of those CAD programs. And those tools typically have a feature that enables you to create 3D models of the robot parts. You would then export the 3D models as mesh files in formats like STL or DAE, and those files would contain information about the robot shape, including vertices, edges, and faces. And then if needed, you can use a tool like Blender, and I'll show you that right here. Let's go back here and let's do Blender file, Blender program for here. Let's see where let's just type Blender. Right there, blender.org. And you go to the download page and you would download Blender. So that's the program that you would use. So it's a 3D computer graphics software tool that enables you to ingest the mesh file and make it simpler, make it a lot more lightweight for your requirements, things like RViz. So you would then add the simplified mesh files after doing some post-processing in Blender to your URDF file to visually represent what the robot looks like. So let's pull these meshes right now off of GitHub. I'm going to close all that. Let's go in here and let's go CD downloads. Okay, and let's do git clone. Since we're running ROS2 Jazzy, we'll do the Jazzy branch. Let's do https://github.com/automatic Addison/my cobot_ros2.get. So we're going to download this repository to our machine. Let's click enter. Let it finish. It's a lot of files. So we'll take a second here. Just be patient. Your download may go faster if you got a faster internet connection. I'm on an office internet connection right now that's running a little bit slower than usual. Okay, we have downloaded everything. So let's clear, go back to the top, and let's copy the mesh files for the robotic arm that we downloaded. Let's copy them into our own workspace. So we're going to do CP space -R for recursive. So we get the whole folder. So my cobot description, meshes. We want everything. Okay, with that asterisk. And let's put it in the ROS2 workspace source, my cobot ROS2, my cobot description, meshes folder. Press enter. All right, and let's check that everything copied perfectly. We're going to go ls ROS2 source, my cobot ROS2, my cobot ROS2, my cobot description, meshes, my cobot 280, and visual. And there we go. Your files are in there. Mesh files are in there, looking good, in your workspace. And you can see that the mesh files, the DAE files, and the corresponding PNG files are all in sync in your workspace. Okay, now let's clear. Clear. And let's move to our workspace. Let's do code period. Type our password. Okay, my cobot, let's close this, my cobot description. And let's open up the CMakeLists.txt. And let's just make sure everything looks good. Okay, and let's add a new package here. I'm going to add let's do find underscore package. And let's add URDF tutorial package, which we'll need later. Okay, and let's go over here. And let's see, let's add our folders so they can be visible. So we're going to I'm going to add a comment here, copy the necessary files to designated locations in the project. And let's do install directory launch meshes URDF RViz. Let's do destination share and then project name. Save. Okay. Want to tell CMakeLists about the folders that we have in here. And do we have everything? We've got meshes. We've got URDF. We don't have the RViz yet. So let's do a right click, new folder. Let's call RViz. And do we have launch? No. So let's right click, new folder. Let's do launch. Okay, we've got all our folders in there. Save it. Looking good. Okay, so let's close that out and let's now configure the package XML. Okay, we've got our package XML open. And let me just take a close look at it just to make sure we've got everything in here. So here, format, my cobot description, version. Let's add a description here. It's good practice. So I'm going to say contains the robot description files that define the physical aspects of a robot. Okay, comma. Let's go back up to the top of a robot, comma, including its geometry, kinematics, dynamics, and visual aspects. And save. Okay, I'm in CMake, and we have to add URDF tutorial dependency. URDF underscore tutorial. Okay, I think we've got it all. Okay, now it's time to build the package. We're in our workspace, and let's type the magic command that will automatically install all the dependencies of our package. Specifically, we need to make sure we download the URDF tutorials dependency, and let's type the command now. So it's ROS dep install -i, and then from path src, okay, and then -- ROS distro $ROS underscore distro, and then -i. So you can see up here, we executed the command sudo apt-get install ROS Jazzy URDF tutorial. That's automatic because what this command here does, ROS dep install I from path source, ROS distro y, it scans the package.xml files to see what dependencies are not yet installed, and then it installs them. And then you get this message down here when everything's done that says all required ROS deps installed successfully. Let's clear. All good. You can run that as many times as you want. So now we need to build, and we'll type build. By the way, I'll show you what build alias does. Again, cd ROS2 workspace, and then :build, and then source the current terminal session by doing source --rc. So let's go clear and let's type build. Everything built fine. Now let's create our URDF file. We will actually create it in XACRO format. I will use the terms URDF and XACRO interchangeably going forward. Remember, XACRO files are like blueprints for URDF files, using macros and variables to simplify complex robot descriptions. Imagine XACRO as the architect drawing up plans, and URDF as the final, ready-to-use construction document. Both file types represent the robotic arm, but XACRO offers more flexibility and organization. Before a ROS tool or component can use the information in a XACRO file, it must first be processed or translated into a URDF file. This step allows for the dynamic generation of robot descriptions based on the specific configurations defined in the XACRO file. So to begin, I want you to open a terminal window like I have here, and let's type this command to create all the files we need. This is a single command. Remember, slow is smooth, smooth is fast. Follow along with me, keystroke by keystroke, click by click. Go slow so that you can go fast. So here, let's do it now. Touch, TOUCH, space, tilde, /. Let's do our ROS2 workspace, source, my cobot ROS2, my cobot description, URDF, mech, and then let's add our files. We're going to do G underscore shape underscore base underscore V to underscore 0 dot URDF dot XACRO, comma, adaptive underscore gripper dot URDF dot XACRO, comma, my cobot underscore 280 underscore arm dot URDF dot XACRO. So take a look at that command. This touch is going to create these how many files we got here? We have 1, 2, and 3 new XACRO files, URDF files. All right, and let's do a space. Let's do a tilde, and then ROS2 source mycobot ROS2 mycobot description URDF robots mycobot underscore 280 dot URDF dot XACRO. Enter. Okay, let's just verify that we've created that. So we're going to go to CD ROS2 source mycobot ROS2 mycobot description URDF mech. And there's our 3 new files. All right, and let's go back again. Let's go to the robots folder. And we've got our new file in there. So we created 1, 2, 3, 4 files using this single command right here. This single command. We created 4 files. 3 XACRO files inside the mech folder inside URDF, and 1 XACRO file inside the robots folder of the URDF folder, which are all inside the mycobot description package. So let's clear everything out. And what shall we start with first? Let's start with the gripper. So let's go back here to the URDF folder, and let's go into mech. And we've got our adaptive gripper right there. So let's do get it, graphic editing tool for Linux, and adaptive. And here we have a blank XACRO file, blank XACRO file. Okay. So now what I'm going to do is I am going to copy and paste my existing code URDF file for this into here. See if this works. Yep. Okay, we're going to save. I'm going to walk through all of this later. Don't fear. Addison is here. We will go through this together. All right. So let's close that. This is the URDF for the gripper, the robot model for the gripper. Now let's do the base of the robot. So get it, G shape base. Remember these URDF files, you will often, especially if you get a robot like Finnick or Universal Robots or ABB or Canova, a lot of different robotic arms out there. And remember that when you are creating the URDF file and you're organizing the files in your own ROS2 package, you're often going to be using off-the-shelf URDFs that are created by the actual manufacturers of that robot. So that's why we can get away with just copying and pasting here. It's pretty much similar to what you'll be doing in a real production level robotic arm project, unless you're making your own custom arm. In that case, you can create it from scratch. All right, so let's copy and paste. Got another screen over here, so let's copy that into here. This is for the robot base, robotic arm base. All right, let's close that out. And okay, so that's there. All right, so next is we want the actual hardware of the arm. Okay, let's clear again. Let's do an ls. Now let's open up mycobot 280 arm. It's blank. Save it. All good. Let's close. Okay, now let's go to robots. URDF. What's in here? Let's go to robots. Let's clear that out. Let's open up this file. Save. Okay, so those are our 4 files that we have filled in. So there we go. Now let's walk through each of the URDF files step by step so we can understand what is going on. All right, I'm going to clear. Let's go to back here. Let's start with the gripper. CD Mech. You know, this is going to be easier if we go over to, let's see how it looks when we open it up in Visual Studio Code. So we've got highlighting and syntax highlighting. So I'm going to do code. Let's type our password. Okay, let's go down to URDF mech. That's pretty good. Okay, so we can walk through it from here. All right, so this is the gripper. This is the gripper. So at the very start right here, we begin with our XML declaration and our robot tag. So these are the lines that you'll find in pretty much any standard URDF file right here. And this XACRO namespace right here tells us we're using XACRO macros for more maintainable robot descriptions. And if you want to learn more about what XACRO is and what it means, XACRO ROS2. Okay, you just go through here. There's some very basic tutorials here on the ROS2 main website right here. And you'll get to it by just typing in XACRO ROS2, and it'll typically be your first example right here. If you want to just learn what XACRO is. But in a nutshell, what XACRO is designed to do, it's designed to make sure that your URDF is not a mile long or many kilometers long. It reduces the amount of code you need to write in each URDF file. Okay, so it's like a macros, consolidating all the code into really tiny, modular, reusable chunks. So this XACRO right here, it tells us that we're using XACRO macros to create a maintainable, shorter robot description file. All right, and here you can see we start off by defining a block of properties. Right here, we've got our joint effort, joint velocity. Remember the joints. Remember the joints. The joints are where the motors are in your robotic arm. Just like in your shoulder, your arm. You've got the elbow joint. You've got the shoulder joint. You've got the wrist joint. And so we define some standard properties that we're going to reuse for multiple joints throughout the robot. The effort, the velocity, damping, and friction. All right, right there. And so those values control how much force our joints can exert, the effort, how fast the joints will move, right here, joint velocity, right here, radians per second, and then their friction and damping characteristics, how much friction and damping they have. And right now I've set it at 0. So think of these as the physical limitations that we're putting on our gripper's movement. Next, we define some mass and inertial properties right here. Kilograms, 0.007 kilograms right there. So these values are very important for accurate physics simulation of your gripper. Next, we see gripper link inertial. What is that? What is this macros right here? This is a reusable template for the inertial properties that we use multiple times throughout the robot. Okay, now we have the adaptive gripper. This is the main gripper definition. And this macro takes some parameters. We can see parent, prefix, and origin. So 3 parameters. So this is the adaptive gripper macro, okay? And it accepts 3 parameters: parent, prefix, and origin. Now, parent is what the gripper attaches to, okay? That's what the gripper attaches to on your robot. Prefix is a namespace prefix for unique naming. And this can come in handy if you've got many different grippers, or you've got different robots on your arm. Maybe you have a prefix left and prefix right. So the gripper for the left arm and the gripper for the right arm. So that's where prefix comes into play. And then origin is where the gripper actually mounts. Now we start with the links. And remember my discussion that a robot arm, or any robot, it's a collection of links and joints. Joints are the movable pieces. Links are the hard, rigid pieces. So the first link that we define in here is the gripper base. The gripper base. Okay, and this gripper base right here, so we scroll down, this is our link. You can see it in all its glory. It has 3 high-level parts: inertial, visual, and collision. Inertial, visual, and collision. Okay, so what is inertial? What does this block define? This block defines the inertial, the physical properties of the gripper base. Okay, origin, where does it connect? What's its mass? What's its inertia? And all of that is defined inside the inertial block. The second block we have is visual, right here. And let's just take a look at this. So visual defines how the actual gripper looks, right there. And I'm going to open up this folder because we can see that we've actually, in our visual section, we're referencing the mesh file that we had copied over earlier. So I'm going to go to that file. Let's go to ROS2, source, my ROS2, my cobot description, meshes, adaptive gripper, visual, and here are our mesh files right here. And we can see that we actually have one for the base. Let's just go over to the side and make sure that's right. So gripper base. And we have gripper base right there. Okay, and then the last section of this link is the collision right here. And a good way to learn all of this, XACROs and URDF, is to actually build a robotic arm from scratch. We're not going to do this in here because in a typical robotics project, you will be using a already manufactured robotic arm, like MyCobot from Elephant Robotics, as I said, or Finnick, or ABB, or Kawasaki. There's a lot of different companies that make robotic arms. So you don't really need to, do all of this from scratch for the most part. So that's why we're just going through what you would do for a real life production level robotics project. So there you go. And then we've got the collision piece, which is the last part. Okay, and we're using just a simplified shape for the collision, a box. We're modeling the gripper base as an actual box with the length, the width, and the height. Okay, and why do we do that? Because it's much simpler for physics engines to be able to handle a box geometry than a complicated mesh geometry. Okay, so you can make it's much more lightweight on different physics engines, like Gazebo. And so that's why we often While for the visual aspect, we'll use a mesh, which has a more complicated geometry, so it looks all pretty and nice. In simulation engines like Gazebo, we use collision, basic collision geometry, a box, a sphere, things like that to make it easier and quicker for these simulation engines to decide if two robots are colliding or not. So remember the visual elements right here, the DAE file. We use the mesh file, and that creates the realistic appearance, while collision uses simple geometric shapes for very, very efficient collision checking. All right. So now moving down, we see our first joint, okay? Our first joint. And this is the joint that connects whatever the parent is, and that could be the end effector of the robotic arm, the last piece, often called the flange, where the gripper actually connects to the robotic arm, flange, F-L-A-N-G-E. That connects to the robot base, the gripper base right here. And so that's our first joint, our first connection right there. And it's actually fixed because we normally will screw on the gripper base onto the robotic arm, right where that flange is. Okay. We've got all these joints, got different links. Just keep going, right gripper, left gripper. And now we get to another and very important joint, which is the gripper controller. And this is the main control point. All right, main control point of the gripper right here, and we define it. And again, if you want to know all the details and the ins and outs and go through each one of these, I highly suggest to use something like ChatGPT or Claude and just get the definitions of each and get a real detailed explanation of each of those. Just in the interest of time, we'll just go through here and show it, but it's definitely worth just getting a more detailed examination of what each of these means so that you know what things to tune and what things to change in case you use a different robotic arm or in case you see this in another URDF file. So yeah, so here you go, all of that. And here's our other joints. All right. Let's take a quick look. Let's take a closer look at, let's see if we've got Mimic anywhere in here. Yeah. Okay, so here's our main control point, which is the gripper controller. All right, and all the other pieces, like the fingers of the gripper and everything, they they're designed to mimic the gripper controller. So in a certain fashion, all right? Because the gripper controller will have a joint, a motor that'll move it. And then there will be other links in there, like the fingers, left 2 and left 1, that will mimic the behavior, the movement that occurs at the gripper controller. So let's take a look at this mimic element right here, specifically for gripper left 2, the gripper base to gripper left 2 joint. Okay, that's the base of the gripper to one of the fingers. And let's specifically look at the mimic joint. So in this right here, the joint, we define for the mimic, we define the name of the joint that we want to mimic for this particular joint. All right, and in this case, we're mimicking the gripper controller. We have a multiplier which scales the movement, and here it's going to be 1 to 1. So you move 5 radians on the gripper controller, you move 5 radians on the gripper base to gripper left 2 joint. And then offset adds an offset to the movement. All right. And so looking at the other fields over here, we've got axis, we've got limit, we've got parent, child, and origin. Let's just describe those real quick. All right. And again, you can get much more detailed by using an LLM to describe, but I'll, on a high level, just explain this. So axis defines which direction the joint rotates. limit defines how far the joint can move in radians. So minus 0.8 radians to 0.5 radians. All right. And then you've got joint velocity as well, how fast it can move in radians per second. And remember, that was defined way up above in our parameters. We developed our XACRO property macros there. So that's the limit tag right here. What are the limits of this particular joint, the motor, okay, that connects the base of the gripper to the left finger, or at least the base of the left finger, which is left 2. You've also got left 1 as well. There's 2 components of that finger there. Now you've got your parent and child relationships right here. This shows how the parts connect. What's the parent of the joint? What's the child of the joint? All right, gripper base is the parent, and it connects to the, so this joint connects the parent to the child. So the gripper base is the parent, gripper child is the gripper left 2. And then you got origin right here, which defines where the joint is located relative to its parent, the gripper base. And that's the same structure for all of these joints, multiple joints in the robotics gripper. And then down here, what is that? What is that gazebo reference? This defines down here gazebo specific element. Remember, gazebo is the simulation engine. Let's just go take a look at that again. Let's type in gazebo ROS 2. Do an image. Okay, and remember, there's gazebo. So this is what it looks like. This is a simulation engine. We'll get a lot of good experience with this later on. But this is how gazebo looks. Creates a very realistic looking simulation environment for your robotic arm. All right, and so here, down here is where we define the gazebo specific elements. So this is particularly right here is a visual tag. We have a visual tag. So we're defining here how this gripper should look and appear in gazebo simulation. All right, and this right here corresponds to a color right here. So this overall structure, all this URDF file does is it creates a gripper with 6 synchronized moving parts. Okay, it's got 3 on each side. It's got gripper 1, it's got a gripper controller, then it's got gripper right 1, gripper right 2, gripper right 3, and gripper left 1, gripper left 2, gripper left 3, symbolizing the gripper. Let's see if you can actually see the gripper. Let's go and say an image of what we actually created. Let's go adaptive gripper elephant robotics. See if we've got a nice, good image of it. Yeah, there we go. Adaptive gripper from my cobot. This guy right here. So you got your gripper base right here. Gripper controller is this connection point, this motor. Okay, and then we've got the right 1, right 2, and right 3 corresponding to this part of the robotic gripper, the actual finger. And then we've got left 1, left 2, and left 3 links, which correspond to the left side of the gripper. All right. That's what we are defining in our URDF file right here. And remember, the gripper's movement is controlled by our single main joint, the gripper controller in here. The single main joint controls it all. And all other joints mimic this joint in a coordinated fashion. Pretty cool. And you can see the multiplier here. Sometimes it's a 1-to-1. So if the gripper controller moves 0.5 radians, for example, this joint will move 0.5 radians. But others, we have -1. So if the gripper moves 0.5 radians, the other one, this particular joint will move -0.5 0.5 radians. Okay, now let's take a look at the gripper base. Pop that open right here. And again, starting at the top, we have the standard XML declaration and robot tag with the XACRO namespace. You see that in all our XACRO URDF files. It's the same setup as the previous file. Now this file defines a single macro called G-shape base. And this G-shape base takes two parameters, the base link, which is the name of the base link, and a prefix for unique naming. So you may have one for the left arm and one for the right arm. Now in this macros, we define a single link with standard URDF components. The inertial, the visual, collision, inertial, a visual, collision, inertial, visual, collision. Those are the three parts of our link. And we discussed that in the previous section where we talked about the gripper. All right. So, origin, the position, X, Y, Z, and orientation, roll, pitch, and yaw of the link's center of mass. The base's center of mass. We have the mass of the link, 0.33 kilograms. And we have the inertia right here. And that inertia describes how the mass is distributed. It impacts how the link resists rotational motion right here. That's the inertia piece. So what does this tell us? This tells us that the center of mass of the base is at the origin. The origin, 0, 0, 0, 0, 0, 0. It's at the origin of the link. Our mass in kilograms, and then our inertia right here. Our inertia matrix values right there. And then we have a visual component right here, defining the mesh file for how the gripper base should looks. We have our geometry, defining the shape of the link, and we define it here using the mesh file that we imported earlier. And then we have the origin for the visual component of this link, which defines the position and orientation of the visual representation. And I'll offset a little bit to make it look nice and pretty in visualization, like RViz or Gazebo. Now, the collision geometry right here, remember that defines the geometry that is used to detect if the particular link collides with an object or another part of the robotic arm in a Gazebo environment. That's what's read here in the collision piece. And we have the geometry piece, and we define this as a basic box shape, length, width, and height. Length, width, and height. And this is in meters. It's a box dimension in meters. And then the origin right here, which it aids in how we position that collision geometry within the link. And then finally, we have the Gazebo specific section where we define how the base appears in simulation. And this 0.5, 0.5, all these 0.5s, this is the color piece. And 0.5, that actually corresponds to gray coloring. So this file right here is much simpler than the gripper because it's just describing a static base piece. And let's see if we can find that. Let's go G-shape base. See if you can see how that looks. G-shape base, my cobot, arm, elephant, robotics. See if we can see that puppy. There it is in all its glory. This is what we're defining right here, this G-shaped base. Right here, this base. G-shape base version 2. You can see a little video of it. Okay. That is the base that we defined. We got the mesh file from Elephant Robotics themselves. Thank you, guys. So much simpler than the gripper, just a static base piece, no joints, no moving parts, just a gray platform that other robotic components, robotic arm can connect to. It's that gray component we saw in the image. Let's close this out. All right, and now we've got my Cobot 280 arm. And this is the arm. And at the top, we begin by defining the XML, the XACRO, just as we always do. We start with the common joint properties. These will be used for all the moving joints in the robotic arm. Okay. It's quite similar in structure to the gripper, but we've got a lot of joints here, much more stronger effort, velocity values for our arm. Okay, and these values right here are used for all the moving joints in the arm. So effort, what is that? What is that effort value? This is the maximum force the joint can exert. Okay, down here, joint velocity. This is a maximum joint velocity in radians per second. We got joint damping coefficient and the joint friction coefficient. And I've set these to 0. Then we define the masses for each link in the arm. All right, and we've got 6 pieces, 6 links of our robotic arm. Let's just take a look at this. Let's see what this arm looks like. Let's go to Google, do my Cobot 280 arm, so you can see what the real deal looks like. The real deal Holyfield. Let's open it up, and here's our arm right there in all its glory. Okay, you can see the different pieces, how the different pieces connect. I think it's kind of hard for you to see that. See if we can zoom in. Yeah. So we've got the dimensions. This is pretty cool because this actually shows the dimensions of each of the links. And you can see the separation. See if I can zoom in. You can see the separation between the links. Link 1, link 2, link 3, 4, 5, 6. All the different links that make up the MyCobot robotic arm, which is a total of 0.85 kilograms. Okay, let's go back. So we've got the mass of each piece of the robotic arm right here. Link 1, link 2, link 3, all the way up to link 6, which is at the top of the robotic arm near the end effector. And this connects to the flange. The flange is that piece. Let's show you again. Let's just keep it open so we don't have to go back. Let's do my Cobot 280 arm. Doing images. Let's open it up. So that's the flange right there. That's the flange. That's where the gripper connects to the robotic arm. And here are our links. Okay. Here are our links right here. All the way up. Here's what it looks like. Let's see if we can find an image. So this base, okay, here's the actual robotic arm. I was trying to find a photo to show you. Well, I'll just explain. Let's go over here. This base goes underneath the MyCobot 280. Okay, this clamps the base onto the table. And this robotic arm sits on top of the base right here. And you can see again the links. Let's close it out. Let's minimize. So we've got the mass of each link. Remember, it's 850 kilograms roughly for the whole robotic arm without the gripper. All right. So now we've got 2 helpful macros in this file. We've got link inertial right here, this macros link inertial, and we've got material visual. So what does link inertial do? What does link inertial do? This is a template for defining the inertial properties of links. So the purpose of having this macro, so we don't have to repeat this block right here for every single link. Again, the purpose of XACRO is to make sure that your URDF files stay nice, maintainable, and reusable. We don't want these massive, gigantic URDF files. So that's where your macros, your XACRO macros, comes into handy. And we define two of these. One to handle the inertial properties, and another to handle the visual properties. Okay, specifically, how will each link appear in Gazebo simulation? Okay. So now we dive into the main robot arm definition. And this macros is called MyCobot 280 arm. And it accepts these parameters. All right. It accepts the base link name, the flange link name, the prefix for unique naming, and then the origin. So for each link, link 1 through link 6 plus the flange, we define the link name, okay, the physical properties using link inertial macros, the visual properties, and we tag the appropriate mesh file to define how this will actually look, and then simplified box geometry, length, width, and height for the actual collision detection. All right, and here are our links, all the links, link 6, link flange link, and so forth. Now we get to the joints. And so the joints connect all those links together. So remember, the links are the rigid pieces of a robot. They're the rigid pieces of the robot. And what connects these one link to the next is a joint, a motor. Okay, and it's the motor there that causes the robotic arm to move, the wrist to move, the elbow to move, the shoulder to move. Okay, so in our file, we now need to define the joints. We've got the name of the joint, okay? And by the way I do it here is for the name of the joint, I actually name it with the parent, name of the parent link of the joint, and the name of the child link of the joint to make it easy to understand exactly what this joint is doing, okay? So this particular joint connects the base link to link 1, then link 1 to link 2, then link 2 to link 3, and so forth, okay? And now we have the type of the joint. So base link to link 1 is just a fixed joint. There's no motion at all. But here from link 1 to link 2, let's go back over here, link 1 to link 2, right here. This is a revolute joint. Because we rotate, revolute means rotation. We have rotation right there in this joint. It is not fixed, okay? So you can have a fixed joint, which just remains constant, does not move. You have a revolute joint, okay, which means you have a rotation, all right? So remember, fixed joint means no relative motion between connected links. Then you've got your parent and your child, okay? This links this shows the links that the joint connects. And we've got our origin right here. Position and orientation of the joint relative to the parent link. And if we dive a little deeper into the joint, you see our fields. We've got limit, parent, child, origin, all that, dynamics, axis. So axis defines the axis of rotation right here. And 001 means we have rotation around the z-axis of the parent coordinate frame. So 001, that's X, Y, Z. So we rotate around the z-axis of the parent coordinate frame. This is link 1 and link 2 joints. So the parent coordinate frame is what? It's link 1. And the limit, this parameter defines the motion limits. the motion limits. Okay. And the motion limits include the effort, which is the maximum torque the joint can apply. Okay, and remember, torque is the twisting force that makes something turn or rotate. And then we've got our lower and upper limits right here, which are the range of allowed angles in radians, allowed angle in radians. And then over here, we've got the maximum angular velocity. I'll go over here so you can see it. Joint velocity, this is the maximum angular velocity in radians per second. Down here, we've got our damping. And what is damping? Damping is this is the parameter measured in Newton meters per radian per second. So Newton meters per radian per second. And this determines how much the joint resists moving at a certain speed. It's similar to how a shock absorber in a car slows down the movement of the wheels when you go over, say, a speed bump. So that's what damping is. Newton meters per radian per second. That's damping. All right, and let's go all the way through the joints here. And down at the bottom here, at the bottom, we set the visual properties for each link and how it should look in Gazebo. And 0.5, 0.5, 0.5, in general, that stands for the color gray. And then 1 stands for the color white. So we can see that the base link, the base and the flange are both gray with the 0.5, 0.5, 0.5, and the links are white. So this URDF describes the complete 6-axis robotic arm, okay, with realistic mass and inertial properties. We've got detailed 3D meshes for visualization. We've got simple collision geometries for the physics used in physics simulators like Gazebo. We've got the joint limits. Let's go down and see that. The joint limits and dynamics. All right. And then we've got the consistent materials section, which helps to notify Gazebo how this robotic arm should look in a simulation environment. Okay, now let's take a look at the file that brings everything together. Go under the robots folder and click the mycobot 280 URDF.XACRO file. All right, this is the file that brings all those components together. All right, let's go to the top. So at the top, we define several arguments that control how the robot is configured right here. Got add world, robot name, base link, base type, flange link, gripper type. Okay, let's start with the add world. So the add world is whether to add a world link, okay, a world link to our URDF. This is very common when you're just testing the robotic arm in isolation, you know, and not connected to anything like a torso, you know, on a humanoid robot. So in this case, we're just doing a standalone robotic arm, so we make the add world parameter true. Okay, base link is the name of the base link of the robotic arm. Then we have base type, which is the type of base to use. Then we have the flange link, which is the name of the end effector, name of the end of the arm, name of the flange. That was that gray part that I showed you right here. This little gray part at the end where you would connect the gripper. Then we have the, let's see what else we have here. Gripper type, and we're using the adaptive gripper from Elephant Robotics. Prefix for naming, we left that blank, but this is commonly used when you're dealing with, say, a dual arm robot. We might want one for the left and one for the right. That's where you'd want a prefix. Then whether we want to use a gripper or not, Sometimes you may not want to use a gripper. You just want to see how the robotic arm moves without the gripper. That's fine. All right. And then use gazebo, false. Use camera, false, and so forth. So we'll cover the camera and gazebo later. Okay, now let's go to this piece right here, this block of code, this if statement. And what does this say? Well, this says if the add world parameter, is true, we need to create a world link to connect our robot to it too. That's a virtual joint. It's not a like real physical joint. It's just a virtual joint between the world and the base link of the robotic arm. And it's connected at the origin of the world. The base link is connected at the origin of the world Now we handle the base. Okay. Instead of the current base is G-shape. Okay, that was that gray platform to which we connect our robot to. Then we need to include it, the G-shape base right there. Okay, and there might be situations where you don't want that G-shaped platform, you just want the arm. In that case, then you wouldn't need any kind of base. But in this case, we've got our standalone robotic arm, so that's what we're doing. And let's see what else we got here. We have the use gripper right here. If we want to use a gripper, we can add it right here in this block of code. And current gripper, I say if it's adaptive gripper, then add the adaptive gripper URDF. So this is it. This is our main assembly file, bringing all of those parts together. We've got the optional world connection, the base, the whole 6-axis robotic arm. We've got the optional adaptive gripper. So each component is included as a separate file and configured using the arguments at the top of the file. So this modular approach, how we did it, it makes it easier to swap out different bases or grippers or create multiple robots with different configurations or create a, let's say if we want to create a humanoid robot, we want to have a left arm and a right arm. It's very modular, very flexible, and it allows us to do that. So that's a detailed walkthrough of all the XACRO files. We've covered everything from declaring the robot model, defining the links, defining the joint, setting up the properties, the mimics. So XACRO files, don't be intimidated. Please don't be intimidated. They look complex the first time you see one. I remember the first time I saw one, I was like, oh my gosh, this looks like Greek hieroglyphics. I'm scared. But don't. Just break it down into small pieces. If you have to use a tool like ChatGPT or Claude to kind of break it down even further and understand each piece, there's no shame in that game. There's no shame in that game at all. You know, I think breaking them down in their components helps to understand how each part contributes to the robot functionality. So don't be scared of these. And again, a very good exercise to do is to build a URDF from scratch so you understand how everything's built from the ground up. And that'll enable you to be able to more easily, I don't want to say easy, it's not easy, but more readily tweak different things in your robotic arm as you would like. When you know everything know all the fundamentals and how it's built from the ground up, you can more easily troubleshoot and identify where things go wrong. And I've got different tutorials on my website just building very, very basic URDFs from scratch, all the way from scratch. Okay, now let's get ready to build the package. Let's close out everything. I'm going to go to File, Exit. It's clear. Let's build. Everything built. And let's see the URDF in RViz. I'm going to launch the URDF file. The conversion from XACRO to URDF happens behind the scenes, so you need to be sure to type the correct path to your XACRO file. Let's do it now. ROS2 launch URDF tutorial. Display .launch.py, and let's do model equals home Ubuntu ROS2 underscore WS src my cobot ROS2 my cobot description. Okay, URDF robots, and then my cobot. Let's enter. And we have an error. Okay, we've got a bunch of files that don't yet exist. Okay, so it says the gazebo sim ROS2 control. Okay, that is because we have not yet created it. So let's go over to ROS2 source, my cobot description, URDF, robots. Oh, it's opening it in an editor. Let's open with gedit. Okay, and it's screaming at this guy right here and this guy, all our control stuff. So let's set use gazebo. Let's see, we've got it at false. Why is it screaming? Okay, let's get rid of this stuff for now. We'll add it back in later. And we don't yet need this either. Okay, so here's our robot file. I'm going to get rid of this stuff that we don't need. We'll add it back later. I'll show you how to do that. Let's just save, X out, X out. It's build again. It's clear. Okay, so I got rid of the camera, got rid of all that ROS2 control stuff and gazebo stuff. All right. And here is our URDF in all its glory. Okay, so this is what your screen should look like, your RViz. Let's uncheck the TF box for now. You can zoom in, use the middle mouse button. Use the left mouse button to change the orientation. Middle mouse to zoom in and zoom out. If you want to change the position, you hold down. I've got a mouse which has a middle mouse roller button. You hold that down and you can move around the robot, the position. Okay, and we can use this over here to move the robot. This is joint state publisher GUI. Up, down, up, down. Right here. Up and down. Let's try this. Try that. Moving the gripper in and out. Left, right. Left, 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 right, left. Get on up. Get on up. Get on up. Board barge. Left, left. All right, so on the left panel, we have our displays panel, and you can just play around by checking and unchecking the different options. For example, under robot model here, you can see how the mass is distributed for the robotic arm. Okay, so we're going to uncheck visual enabled and check collision enabled. Okay, and under mass properties right here, we're going to check mass. Uncheck collision enabled so you can see the mass here. You can see the mass, how the mass is distributed for the robotic arm. Okay, and let's collision enabled. Let's undo the mass. And here you can see the collision geometry for the robotic arm. Okay, you can see it's a simplified version of the robotic arm composed of boxes and cylinders. This makes it much faster for tools like Gazebo to calculate collisions. Let's check the robot model again for visual enabled, and you can see how the collision geometry syncs up with the actual robot. There's our base, that rectangular base. Here's the base of the robotic arm right here, and then all the links. The kinematic chain is what we call it in robotics, all the way to the gripper, the flange and the gripper. Now let's check out the coordinate frames. Let's open a terminal window. Let's go to CD Documents. Okay, and let's do ROS to run TF2 underscore tools, and then view frames. Enter. Wait 5 seconds. We want to see the coordinate frames. All right, you're going to see a bunch of gobbledygook text coming out. Let's clear all that. Let's do a dir. And now do events, frames. Okay, events frames. We're going to open this PDF file using events. And here is what we see. Let's expand that out. Okay, you can see our world coordinate frame, which we included. We have our base link, and then our kinematic chain from link 1 all the way through the flange of the robot. Okay, and then the gripper base, and then the gripper base connecting to all of the different parts of the robot. Okay, let's Control C. To close RViz, we're going to close everything. You can see RViz here. We're going to go to the terminal. Let's do Control C to close it all. And so that we can quickly visualize our robot in the future, let's add a bash command that will enable us to quickly see our URDF. Okay, and I'm going to do echo. Let's call it alias elephant equals single quote ROS to launch URDF tutorial display.launch.py model colon equals home Ubuntu ROS2 underscore WS SRC my cobot underscore ROS2 my cobot underscore description URDF robots my cobot underscore 280.urdf.XACRO single quote double quote, and then the 2 arrows, and then we're going to do bash.bash rc. Press enter. Okay, my enter is not working. Let's try it again. Let's see, what am I missing? Echo alias ROS to launch single quote quote bash rc. What's going on here? Alias. I see what the issue is. Okay, let's go back up and let's get rid of that double quote right there that we have after elephant. There we go. Okay, so now if we do alias, Oh, we got to source the bash RC first. Source ~/.bashrc. Now we type alias, and there we go. You can see it right here. ROS2 launch, URDF tutorial, display.launch.py, and then model, and home Ubuntu ROS2 WS, source, mycobot _ ROS2, mycobot description, URDF robots, and then the name. So let's do a build. Okay. Source, clean everything up. And now let's see our robot again. Elephant. Type the alias, elephant. And there we go. So now when we want to see our robot, all we need to do is type elephant in the bash or in the terminal bash session. And we've got our robot. We can move it around. Pretty cool, huh? Beautiful. Take off the TF. There's our robotic arm in all its glory. So that's it for this tutorial. Thank you for following along. Thanks for watching. Keep building, and I'll see you in the next tutorial.